Dear members of the organizing committee, dear participant of the conference, it is a pleasure to deliver this lecture about this amazing infrastructure project in which my institute and myself are involved since almost 1 decade. There are a lot of interesting aspects about this project. Today I will focus on the advanced numerical modelings that we did to investigate the settlement behavior of the new railway station, which is called in Germany Stuttgart 21. The time is very short, but I will try to give you a short overview about the high-speed railway project Stuttgart-Ulm. Then I will describe a few distinguishing aspects of the new station, which is crossing a river valley. And finally, I will shortly describe the subsoil conditions, the foundation concepts, the numerical model we did to model the deformation behavior of the station, and present few selected results. The new railway will connect the cities of Stuttgart and Ulm. Considering the already existing new line between Ulm and Munich, it will allow a reduction of the travel time between the state capitals Stuttgart and Munich to about 75% of the current travel time of 2 hours and 20 minutes, and motivate probably many people to use the train instead of the car. It is worth mentioning that the project is part of a 1,500 kilometers European high-speed railway linking important cities from 5 different countries between Paris and Budapest. This is a project overview. The dark line is the existing more than 100 years old railway connecting the city of Stuttgart and Ulm, which is following the highly complex mountain relief and do not allow high-speed transit for this reason. The new railway in red, with a total length of about 120 kilometers and a maximum velocity of trains of 250 kilometers, can be divided in 2 principal parts. The new railway connecting the city of Wendling with Ulm with the yellow frame, within the yellow frame, and the reorganization of the railway node Stuttgart in the green frame, which includes the new station Stuttgart 21. The construction in highly populated areas, the environmental constraint and restriction in and around Stuttgart, and the geomorphology of the region make this project extremely complex and challenging, not only from the engineering point of view. One proof of the technical complexity is that more than the half of the alignment consists of tunnels and bridges. The city of Stuttgart is placed in a valley surrounded by mountains, like a vessel with an opening in the northeast. To travel from the west to the east, the railway enters in the vessel, stop in the terminus station, and leaves the vessel to the east. The problem of this alignment is not only the time delay caused by entering in the vessel through the city, but the precious city areas currently occupied by the rails. The new railway will cross the surrounding mountains and the Nessenbach Valley from the west to the east. It will be located in the same place as the old one, but rotated 90 degrees and below the ground level. Here you see the existing terminus station, which is placed in the center of the city, surrounded by different buildings, roads, and parks, and a lot of underground infrastructure, metro lines, sewers, media channels, etc., which of course cannot be seen in the picture. Exemplarily, the red rectangles highlight the State Bank of Baden-Württemberg on the east, on the top, a very sensible building, and two heritage buildings, the old direction of the Deutsche Bahn, the German train company, on the left, and the station, the old station building on the bottom, which has to be conserved and integrated to the new station. The new station is rotated 90 degrees with respect to the old one, as we say before, and will be constructed with the cut and cover method. It consists of the main station hall and two transition tunnels, one on the left and on the right, connecting the station with the mining tunnels. The valley crossing has a total length of 870 meters and a maximum width of 80 meters. The three buildings mentioned exemplarily are also shown in the picture. Especially challenging was the conservation of the DB direction, the building on the west. The 10-story building was temporarily underpinned to allow the tunnel construction underneath, and finally the building will be supported by the tunnel. We see a detail of the valley crossing with the main hall in the center, about 450 meters long, and the north and the south transition with lengths of about 200 meters. The transition tunnels are more or less conventional cut and cover concrete boxes. On the contrary, the main station hall is an architecturally and structurally very demanding and special construction. We will see into more detail in the next lecture. Here you see the station consisting of a roof which is supported by a throat and by 24 columns with the shape of a calyx, as you are seeing in the picture. The roof is a reinforced concrete shell with a thickness varying between 0.3 meters and 1.5 meters and does not contain any joint over the complete length of 450 meters. The base of the structure will be around 14 meters below the present ground level. The roof was designed by star architect Christoph Ingenhofen, and the structural part was made by the engineer Werner Sobeck. According to the architectural design, the concrete structure will not be painted. Instead, a special white concrete was developed and used in construction. The construction of the columns is extremely challenging. First, the toe of the column is constructed. You can see here the toe and the scale in comparison with the person beside the column. Then the upper part of the calyx column are constructed, and after finishing this construction, the column is temporarily supported as you see in the picture. The gap between the columns is closed after finishing adjacent columns. Here you see the current progress of construction with several columns already finished and some gaps being in the process of closing. Finally, I would like to present a short animation of the station from the perspective of a train traveling from the transition tunnel into the new station. You see the columns, and you see the openings on the top of the columns allowing the natural light to enter in the station, and during the day it will allow to illuminate the station without any electrical necessity. The geology in Stuttgart consists of several sedimentary Jurassic and Triassic formations which are partially covered by quaternary sediments in the valley. This formation consists of sandstones, siltstones, claystones, marls, and gypsum upon limestone. Near the surface, The rock formation can be slightly to strongly weathered. In some places in the valley, completely decomposed to residual soil. Beside the quaternary aquifer, there is a second aquifer, an artesian mineral water aquifer in the limestone, which is intensively exploited in Stuttgart, and therefore it is important from the economical point of view for the city. The protection of the mineral water aquifer imposes several restrictions to the project and is conditioning the construction of the station strongly. Owing to the heterogeneous geological conditions along the valley and at the flank of the hills, the geotechnical properties are also varying along the station. Most part of the whole lies on fluviatile sediments and decomposed sedimentary rock. The north and the south transition and a part of the whole will rest on weathered clay and siltstone. The main requirements of the foundation are to limit the deformation and differential deformation of the roof structure and the railway, to avoid damage of underlying underground structures, and to ensure water tightness. To fulfill these requirements, accounting from the geotechnical conditions and the restriction to protect the mineral water aquifer, a mixed foundation was selected. The calyx columns and the walls are founded on bore and Franke piles. Between the columns, the loads are transferred to the ground by the slab directly. Additional piles are arranged between the columns depending on the soil stiffness and to bridge underlying structures and to reduce, of course, settlements. For different reasons, which I will not be able to explain in the short of the time, the station has to be constructed in 20 sections. The construction process includes several different construction stages taking place in different sections at the same time. To realistically predict the deformation of the station and the rails, as well as the influence of the station on the underground structure and neighboring buildings, a 3D finite element model considering the soil foundation structure interaction in detail and the construction process was developed. Here you see the finite element model at the end of construction. The area is about 1 square kilometer. The depth of the model is about 80 meters. The model is considering the real topography of the valley and its flanks. For the simulation, we use the program Simulia Abacus. An elastoplastic continuative model similar to the hardening soil model was implemented as user element and used to model the behavior of the relevant geotechnical units. The model has more than 1 million degrees of freedoms. The slides show screenshots of the station hall, the north and the south transition, and the ground models. As you can see, underground structures and buildings which will be constructed on the north and south transition are considered in the model. The structures composing the station were modeled in detail. In this slide, you can see the hall and the transition tunnels, the beginning of the mining tunnels, underground structures and facilities, and several buildings on the top and beside of the north and south transition tunnels, which will be constructed after the station has been finished and will cause, of course, additional deformation of the structure. The interfaces between the structure and the ground are modeled with contact surfaces with the Coulomb friction law. In the 3D model, every single pile, including no linear low settlement behavior, has been modeled. The low settlement behavior of the single pile was determined based on the results of pile loading test. The low settlement behaviors depend on the soil layers in which the pile is embedded and on the pile type. To consider the 2,000 piles of the foundation, we developed a new modeling strategy using so-called embedded elements and connector elements. To my knowledge, the size of the model, in combination with the high level of detail of the structure, the foundation and the construction process, and the nonlinear behavior of soil interface and piles, is so far unique. This animation shows you transversal cuts through the numerical model, starting from the mining tunnel at the south, passing through the transition tunnel, the station hall, the transition tunnel in the north, showing the underground infrastructure, the piles, and ending at the mining tunnel in the north. The simulated construction stages can be visualized through a longitudinal cut along the model. As mentioned before, different construction activities take place at different sections at the same time. This has a big impact on the settlements and different settlements of the foundation and deformation of the structure, and of course has to be taken into account in the modeling. These contour plots show exemplarily the settlements at the end of construction for the permanent loads and 1/3 of the service load. The maximum settlements are about 2.5 centimeters. The maximum rotations are less than 1 to 2,000 to 2,000. After constructing the building on top and applying the full service load, the maximum settlement increased to about 5.1 centimeters, but the rotation still remained less than 1 to 2,000. This diagram shows the settlements along the station. On the left side of the diagram, we have the settlement of the transition north. On the right side, the settlements of the transition south, in between the settlements of the whole. The different curves correspond to 3 of 8 rails, 1 in the center and 2 in the edges of the whole. The shadows show the settlements range due to the possible range of parameter variation, soil parameter variation, which were considered in the calculation. The settlements requirement for the rails are very stringent. After installation of the rails, maximum settlements of 1.5 centimeters are allowed. Exceptionally, 3 centimeters can be accepted. As we can see, the first criterion is fulfilled in the station, with exception of the north transition after construction of the building on the top. At this location, the settlements will be measured during construction of the building, and an adjustment of the rails, which is extremely expensive, is planned in the case the settlements will become larger than 3 centimeters. Let us finish with some final remarks. The geological and hydrogeological conditions have strongly conditioned the design and construction of the central station. A 3D model was required for the analysis of the serviceability limit state due to the complex mixed foundation construction sequence, susceptibility of rough structure to differential deformation, and the protection of the existing underground structure. Considering the size of the model, the high level of detail of the structures, the foundation and the construction process, and the nonlinear behavior of soil, interface, and piles, we conclude that the 3D model is so far unique. The observational method has been applied to validate the numerical models and to improve the quality of the prediction during construction. This is a process which is undergoing. I thank you for your attention. I wish you an interesting conference, and I hope we will meet the next time in person. Thank you very much. Bye-bye.